In section 1.7, we're going to introduce the ideas of limits and continuity, two ideas that are going to be fundamental for the rest of the ideas in this course and future calculus courses. So in this section, we're going to understand the definition of continuity and limit. We're going to determine if a function is continuous based on a graph, as well as just based on a formula. We're going to be able to find the limit of a function given by a graph and find the limit of a function using numerical methods. In the next two sections, we're going to look at finding limits of functions algebraically, just given the formula of a function. Finally, we're going to try to understand the intermediate value theorem, which we're going to commonly call IVT. So before we give the definitions of limit and continuity, let's just try to understand what are these ideas in a more general sense. So a function is continuous on an interval if, and we can say any of these things are a way to sort of think about continuity. If the graph has no breaks, vertical asymptotes, jumps, or holes in the graph, and we'll see some examples of those down below in a second. We can also think that a function is continuous if we can draw the graph without lifting the pencil from the paper. Another way to think about that is that if you had a little bug crawl along the function, that bug could crawl along the function without jumping as long as that function is continuous. And then a very general way of thinking about continuity is continuous functions are quote unquote nice functions. That means that there's nothing too weird going on. And in general, most every function that you've dealt with is a continuous function, or at least continuous on its domain, which we'll talk about in a little bit. So let's look at some examples. This first one, x squared plus x, is a quadratic function, and this is continuous everywhere. And by everywhere, we mean all real numbers, negative infinity to infinity. We are talking about x values here. So this function is continuous because there's nothing kind of weird going on. You can draw this graph without taking your pencil off the paper. And if you had a little bug crawl along this function, it could do so without jumping. It could just crawl along that function the whole way through. The next one is not continuous at x equals 0. This is the function y equals 1 over x. And this is not continuous because there is a vertical asymptote at x equals 0. The function approaches that asymptote on both sides, but never actually gets to that line. So let's look at our ways to see why this is not continuous. Again, there's a vertical asymptote, that means it's not continuous. The graph cannot be drawn without taking your pencil off the paper because you could draw one half of it, then you have to take the pencil off and then move to the other half. A bug could not crawl along that function because it would have to jump to that next part the same way as your pencil coming off the paper. And then we say this function is not nice because there's something weird going on. This asymptote is something weird. But also note this function is continuous everywhere else except at that one specific point at x equals 0. Another way to kind of say this is a continuous function. This is continuous on its domain. The domain of 1 over x is negative infinity to 0, union 0 to infinity, and it is continuous on that interval. And that's going to be kind of two different ways of continuity to think about: continuous for every x value, or just continuous on the x values that matter for that function. And both are going to be reasonable ways to think about continuity. The last example here is not continuous at x equals -1 because we have a jump here. And this is called a jump discontinuity. Discontinuity is something where the function is not continuous. And this example is not continuous on its domain either, because -1 is in the domain. So this is something different as well. This is just a discontinuous function. And that's also what we're going to think about. We're going to say that discontinuous or discontinuity is the same as not continuous. All right, so that's an example of a discontinuity, a jump, because we go from one point down to another. Note that this is still a function because this passes the vertical line test because this function only hits that line at that one specific point. All right, there are other examples of discontinuities. Specifically, we have a hole is what we're going to call a removable discontinuity. And that's going to look like some function with a hole like this, or even where that point is kind of removed from there. That is a hole, and that's also discontinuous. All right. So what functions that we know are continuous? And that's going to be almost everything we know. All polynomials, exponentials, sine, cosine functions are continuous everywhere. That is on the interval -infinity to infinity. And note that even though it says sine and cosine, that's any function that involves sine or cosine just by itself as well. Then basically the next group is all the other functions we deal with, and that is rational functions, tangent, secant, cosecant, cotangent, square roots, logarithmic functions. Those are all continuous on their domain. So there's something weird that happens on those special points, not in the domain, but on the domain it's continuous. And a good example of that is tangent. So tangent is continuous on its domain. It's definitely not continuous everywhere. We can say this is not continuous or discontinuous at x equals -3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and there's values to the left and right forever there. And those are the vertical asymptotes here. But it is continuous everywhere else. And that's going to be a useful thing to kind of use. What other functions are continuous? Well, if we take any two functions and we add, subtract, or multiply those functions, then that function is itself continuous. So now you can get some kind of weird functions like e to the x sine of x. That's a continuous function because e to the x is continuous, sine is continuous, so they're both continuous. Division of continuous functions is also continuous, provided that the denominator is non-zero. Then you can get some issue with a vertical asymptote happening. Another big one is the composition of continuous functions is continuous. And there's one more little caveat with that, and that is if the inside function is continuous on an interval I, and the outside function is continuous on the range of g of x, then f of g of x is continuous on I. So let me do an example to sort of show what I mean by that. So here, f of g of x is sine of square root of x. The inside function is square root of x. The outside function is sine. The domain of the inside function is 0 to infinity, including 0. That's the domain of a square root function. So that means that sine of square root of x is not continuous everywhere. It is only continuous, which we sometimes call CONT with a period, continuous on the interval 0 to infinity only. This function doesn't exist past that 0 to infinity. Right, note this is also continuous on its domain. Right, that's a fairly technical part of this, but know that composition of continuous functions are continuous. That's the big thing. All right, so now we have the idea of continuity. Let's think about what a limit is. And the limit is the foundational part of all of calculus. We're going to introduce what a derivative is, what an integral is as well, but all of those are just limits. And this is the big calculus topic that we're going to learn. So a limit is a tool used to understand the behavior of a function near a point. And that is the big word there, near a point. We don't actually care for a limit, what happens at a point. So a limit answers the question, as x approaches a value c, what happens to the function values as we approach that value? So we're going to look at this example, and we're going to do it in kind of two different ways. First one's really not going to be a very interesting example, and the second one will be more interesting. So first off, what is the limit of the function below at x equals 2? So what we mean is, as we approach the x value 2 on both sides, and we look at the corresponding function values, so it's like we're looking at the corresponding function values, and we're seeing what happens to those as we get closer and closer to 2. What value is that approaching? What function value? And this is just going to be the actual function value itself. The limit here would be equal to 1, and this is just the function value. Now, I call this an uninteresting example because the limit itself was just the function value, and that's going to be the case when we have a continuous function, when we have a nice function that we're dealing with. And note that this function is continuous at x equals 2. There's nothing weird going on at that point. All right, so if we get closer and closer to 2 on the x-axis, and we look at the corresponding function values, we kind of trace our fingers closer and closer to that point, we're seeing where that point leads us. All right, so now let's see, why is a limit useful? Because that's not very useful there. We could just see the function value. When we look at the limit of the function below at x equals -1, this is more interesting because there is no function value at that point. Right? We could not ask what is f of -1, because there is no answer for that. It's undefined, it's not in the domain, it doesn't work. So we need another kind of question to ask, what's going on at that point? And we do know kind of what's going on, and we're kind of filling in the hole there. So if we get closer and closer to -1, we can see that the corresponding function values are approaching that hole. If we get closer to -1, look at the corresponding function values. We're getting closer and closer to that hole. And it's like our answer is going to be whatever that function value is. And that's, again, going to be 1. But note that we are not continuous here at x equals -1, sorry. Right, and that makes it a more difficult question to ask, what is the limit? It's like we're filling in this gap in the function. We know kind of what's going on. We know it's sort of getting closer and closer to 1, but the actual function value doesn't give us that information. And even though it goes way beyond that, that's sort of a fundamental idea of why is a limit useful, is we're able to fill in the gaps of our knowledge of these functions. So we just showed how to find a limit graphically. It's this idea of kind of tracing your fingers on the function to see what value we're approaching. We can also do this numerically. So here is a function, sine of x over x. And this is not continuous, at x equals 0. There's some issue there because if we plug in a 0 to that function, it's undefined because there is a vertical, or not a vertical asymptote, but there's a hole at that point. So if we look at this function here, the actual graph, if we approached 0 from the left and the right, the answer to this question is whatever that function value is, whatever that y value is going to be. But we can also do this numerically and find out by just plugging in values closer and closer to 0 and kind of seeing what happens. And if we go back to thinking about what is the idea of a limit, the idea of a limit is what happens to the function near a point. So let's take function values near 0 and let's see what happens. So let's see if we can draw some kind of conclusion. So here's a table of values of x values near 0 or at 0. So we're going to do negative 0.01, negative 0.0010, 0.001, and 0.01. These are all values very, very close to 0. And we can see that all of these values are near 1, and we're actually getting closer to 1 as we get closer and closer to 0. But the actual value at 0 is not defined. So again, this is kind of filling in this gap in the knowledge, saying something about what is that hole and what is the function value at that hole. And we can say that the answer here is going to be 1. And I think we can kind of safely say that those function values are getting closer and closer to 1. If you plugged in 0.0001, you would get even a value closer to 1 than that. All right, and that gives us some information about this function that's very, very useful. And in fact, that we're going to use in this course, that specific limit. All right, I will take a second to make a big note, and we'll say this later on as well. Plugging in points to find a limit is a strategy, but it's a very weak one. Is time consuming and unreliable. So we're going to learn how to do it in this section. We kind of went over it. We'll do another example in the next video. But really, it's not the best way to think about a limit. It's sort of a last resort kind of idea of what to do. And in fact, this is maybe a good example of a function that there's not a great way of doing that algebraically or with the graph. We don't really know what the graph looks like just by itself. So right now, it's an okay strategy to use. But going forward, I'm going to urge everybody not to jump to plugging in values to find a limit. All right, now we can talk about the actual definitions, and we are going to use these as much as possible. So let's start with the idea of a limit, and then we'll do continuity after that. All right, so the wordy definition is, if a function's defined on the left and the right, that just means that everything's defined near that value. We say that a number L is the limit of the function as x approaches c, if f of x is as close to L as desired, whenever x is sufficiently close to c. And we write that the limit as x approaches c of f of x equals L. So this is our notation, this limit notation. All right, and what we're saying is that if we get closer and closer to that x value of c, we can get closer and closer to that value of L. There's some more technical math stuff going on with these words like sufficiently close, right? That is saying if you want to get as close as you want to L, there's some x value that can get you to that sufficiently close to C. In general, basically we're saying what happens to the function as we get closer and closer to that x value. All right, the value of a limit is going to be a single number, and that is the value L, that single number. We could also have answers like infinity, minus infinity, or DNE, which stands for does not exist. All right, note that a function does not have to be defined at the point for the limit to exist. And we actually said before that it's the interesting examples where the function's not defined at those points. All right, limits are more useful when that occurs. Since we already know what the function value is, it's not terribly useful when it's not that way. All right, some technicalities here. Positive and negative infinity are not real numbers. So we have a value of the limit that is positive or negative infinity. You may see that the limit does not exist in these cases. All right, but what we're going to do is we're going to adopt the convention that if the answer is infinity or negative infinity, we're just going to use that as the answer and not DNE because it gives us more information. And we have some kind of idea about what infinity means, so we can use that. A common mistake is to say that the limit is undefined, but this means something different than DNE. So we're going to try to be very careful to not say undefined unless it actually is, which is not going to be the case for any limit that we look at. Undefined would mean that it would not make sense to even ask what the limit is at that point. It wouldn't even really make sense. Maybe it's completely out of the domain or something. It doesn't make sense. All right, that would be that the function is not defined on the left and the right. If that was not the case, then the limit might be undefined. All right, and then finally, I think it's very important to understand this idea of this notation. We're going to use this notation a lot. It's important to understand what it actually means. So limit as x approaches c, f of x equals L is a shorthand way of writing the English sentence, the limit of the function as x approaches c is L, which is itself shorthand notation for saying, as we take x values closer and closer to c, the function values get closer and closer to L. That's what we're saying there. The definition of continuity has to do with the limit itself. We kind of already hinted at this. So if a function is defined on an interval containing a point c, we say that a function is continuous at x equals c if the limit of the function equals the function value. Right, and we've seen some examples of this already, right? We had our example from the first page. That the function value here was not defined at -1. But the limit as x approaches -1 of the function was defined, and that was equal to 1. And since these are not the same thing, we can say that this is discontinuous or not continuous at that point. But when we looked at 2, we found that f of 2 was equal to 1, and we know that the limit as x approaches 2 of the function was also equal to 1. These are the same, so we say that the function is continuous at x equals 2. Note that what this is the definition of continuous at a point. We say a function is continuous on an interval if it's continuous at every point in that interval, right? So we can say that this function here is continuous on the interval -infinity to -1 union -1 to infinity, everything but -1. All right, lastly, we have this intermediate value theorem. So let's just state the theorem. Let's talk about why it's true and how it works. Suppose that f is a continuous function on the interval a to b. So we are requiring that we are talking about a continuous function here. That's a nice function that we're dealing with. There's no holes or breaks. We can draw the function without taking our pen off the paper. If k is any number between f of a and f of b, these are the function values, f of a, f of b, then there is at least one number c in a to b such that f of c equals k. So let's take this picture, let's label a few more things. We're looking at function values here. So here is f of a, down here is f of b, and we're saying that if we take any value in between those two, how about k, then we know that the function value has to hit that value k at some point because we're in between f of a and f of b. And what I would urge you to do to understand this even better is draw a little picture on your paper and label f of a and f of b, label k. So we have a here, f of a, b, and f of b. Draw a continuous function that connects these 2 points any way you want, as long as it's continuous, and try to do so that it does not pass through that function value k. I did not succeed because I actually passed through it twice, it looks like. All right, so the intermediate value theorem says that's supposed to happen, but I urge you to try and convince yourself that you cannot do that because you can't. It's not possible unless you have some discontinuous thing. So how could I do this with a discontinuity? Well, that's pretty easy. Here is an example of a not continuous function that skips over the function value k, right? But as long as I'm continuous, I have to hit that. And that is, again, any intermediate value in between f of a and f of b is hit by a continuous function. That's what it's telling us. And that seems like a very simple idea, and it is a simple idea, but it's useful later on to kind of give us some more complicated results. In the next video, we're going to go over a bunch of practice problems to solidify the ideas of limit and continuity.